Fillers in thermally conductive adhesives, materials, mechanisms, and applications. Adhesives are widely used in modern engineering and electronic applications where they serve both structural and functional roles. Depending on the application, adhesives may require either high or low thermal conductivity, particularly when used in environments operating above ambient temperature. In electronic systems, thermal management is critical because device reliability decreases significantly with increasing temperature. It has been reported that for many electronic components, a temperature rise of approximately 2 degrees Celsius can reduce device stability by nearly 10%. Consequently, efficient heat dissipation is essential for maintaining performance and longevity. Thermally conductive adhesives, TCAs, have therefore become indispensable materials in electronic encapsulation, heat dissipation interfaces, and thermal management systems. However, most polymeric materials used as adhesive matrices, such as epoxies, silicones, polyurethanes, and acrylics, possess inherently low thermal conductivity, typically in the range of 0.1 to 0.3 watts per meter per Kelvin. While these polymers provide desirable mechanical strength, adhesion, and processability, they are insufficient for removing the heat generated in high-power electronic devices. To overcome this limitation, thermally conductive fillers are incorporated into the polymer matrix to enhance heat transfer. The addition of fillers enables the formation of continuous heat transfer pathways within the adhesive. When the filler concentration exceeds a critical threshold known as the percolation threshold, filler particles establish a three-dimensional conductive network that significantly improves thermal conductivity. During polymer matrix curing, resin shrinkage often occurs, bringing filler particles into closer contact. This increased particle-particle interaction further enhances heat transfer, and thus the final thermal conductivity of the adhesive is typically determined after curing is complete. Thermal fillers may be metallic, ceramic, or carbon-based. They can exist at micro or nanoscale dimensions and take various morphologies, including spheres, flakes, wires, and fibres. The geometry of the filler particles strongly influences thermal conductivity because particle shape affects the contact area between fillers and, therefore, the thermal contact resistance, TCR. Spherical particles generally exhibit point-to-point contacts, whereas flake-shaped fillers can establish surface-to-surface contact, reducing TCR and facilitating more efficient heat transport. Inorganic metallic fillers. Metallic fillers possess high intrinsic thermal conductivity and can significantly enhance heat transfer in adhesives. Typical examples include aluminium, copper, nickel, and silver powders. These fillers are particularly useful in applications where electrical insulation is not required because metal particles are electrically conductive. In such cases, thermally conductive adhesives may also function as electrically conductive adhesives. Copper fillers. Copper is widely used for its high thermal conductivity and relatively low cost compared with noble metals. The thermal performance of copper-filled adhesives depends strongly on particle size, morphology, and loading fraction. Studies have shown that copper powders with particle sizes of 50 micrometers, 75 micrometers, and 100 micrometers can enhance thermal conductivity when incorporated into polymer matrices. Generally, smaller particles produce a larger improvement because they provide greater surface area and more contact points within the conductive network. Thermal conductivity increases with increasing filler volume fraction. However, the rate of improvement is typically greater at low filler loadings and gradually decreases as filler concentration increases. Particle morphology also plays an important role. Copper flakes are more effective than spherical particles because their large surface area enables direct contact, reducing thermal contact resistance and thereby forming more efficient heat conduction pathways. Nevertheless, flake-shaped fillers also increase the viscosity of the adhesive due to greater friction between the filler and polymer matrix. Aluminium fillers. Aluminium powder is another commonly used metallic filler for thermally conductive adhesives. Similar trends are observed for aluminium-filled systems as for copper-filled adhesives. Thermal conductivity increases with filler concentration and temperature. However, variations in particle size generally have a smaller influence on thermal conductivity than variations in copper particle size. Aluminium offers several advantages, including lower density and cost compared to copper, making it attractive for lightweight thermal management applications. Silver fillers. Silver exhibits one of the highest thermal and electrical conductivities among metals and is therefore widely used in conductive adhesives. Micro and nanoscale silver particles can simultaneously enhance both thermal conductivity and mechanical strength of adhesive joints. Silver flakes are particularly effective because their geometry reduces thermal contact resistance between particles. In electronic packaging applications, silver nanoparticles dispersed in epoxy matrices form efficient heat-conducting networks that can achieve thermal conductivities approximately twice those of unfilled epoxy systems. However, the high cost of silver restricts its use to specialized high-performance applications. Ceramic fillers. Ceramic fillers are particularly important for thermally conductive adhesives used in electronic devices because they provide high thermal conductivity while maintaining electrical insulation. This property prevents electrical short circuits while enabling efficient heat dissipation. Common ceramic fillers include aluminium oxide, aluminium nitride, ALN, boron nitride, BN, and silicon carbide, SiC. Aluminium oxide. Aluminium oxide is a widely used thermal filler due to its relatively low cost, good electrical insulation, and moderate thermal conductivity, approximately 12 watts per meter per Kelvin. Alumina-filled adhesives are commonly employed in electronic devices such as light-emitting diodes, LEDs, where efficient heat removal is required without compromising electrical isolation. Increasing the loading of alumina in epoxy-based adhesives generally results in higher thermal conductivity, although it also increases the viscosity of the formulation. Additionally, alumina nanoparticles can improve the mechanical properties of the adhesive, such as stiffness and strength. Aluminium nitride, ALN. Aluminium nitride is another important ceramic filler because of its high thermal conductivity, low dielectric constant, low thermal expansion coefficient, and relatively low toxicity. The thermal conductivity of ALN-filled epoxy adhesive strongly depends on filler loading and particle size. For example, when the aluminium nitride volume fraction increases from 0% to approximately 62%, the thermal conductivity of an epoxy adhesive can increase from about 0.2 watts per meter per Kelvin to approximately 4 watts per meter per Kelvin. Similarly, adhesives containing about 78% aluminium nitride particles, approximately equals 5 micrometers, may exhibit thermal conductivities more than 10 times greater than that of unfilled epoxy. Boron nitride, BN. Boron nitride possesses higher thermal conductivity than alumina and is widely used in thermally conductive adhesives requiring electrical insulation. Hexagonal boron nitride, HBN, has a layered structure that facilitates efficient heat transport along the plane of the layers. BN fillers can form aggregates within the polymer matrix, thereby enhancing heat conduction pathways. Importantly, effective improvements in thermal conductivity can often be achieved at relatively low filler concentrations, thereby minimizing increases in viscosity. Silicon carbide, SiC. Silicon carbide is valued for its excellent thermal stability, high hardness, corrosion resistance, and ability to withstand temperatures up to approximately 1000 degrees Celsius. These properties make SiC particularly suitable for high-temperature adhesive systems. Even small additions of SiC nanowires can significantly enhance thermal conductivity. For example, incorporating 3 weight % SiC nanowires into epoxy adhesives can increase thermal conductivity from approximately 0.423 watt per meter per Kelvin to around 0.449 watt per meter per Kelvin. Furthermore, combining SiC with other fillers, such as graphite, can yield synergistic improvements in heat transport. Carbon-based fillers. Carbon-based materials are widely studied as thermal fillers because they combine high intrinsic thermal conductivity with low density. Common examples include graphite, graphene, carbon nanotubes, carbon fibers, and diamond powders. Graphite powder. Graphite is an important filler due to its high thermal conductivity, layered structure, and relatively low cost. Lamellar graphite particles can easily form interconnected pathways within the polymer matrix, resulting in efficient heat transport. In epoxy systems, thermal conductivity can increase from approximately 0.17 watts per meter per Kelvin for unfilled resin to around 1.68 watts per meter per Kelvin when approximately 44 weight % graphite powder is incorporated. Graphene. Graphene possesses exceptionally high thermal conductivity, ranging from about 600 to 5000 watts per meter per Kelvin. Due to its atomically thin layered structure, graphene sheets can efficiently form three-dimensional heat conduction networks within polymer matrices. Adhesives filled with graphene often exhibit higher thermal conductivity than those containing conventional graphite or graphite nanoflakes. Consequently, graphene is increasingly investigated as a next-generation thermal filler for high-performance TCAs. Carbon nanotubes, CNTs. Carbon nanotubes exhibit extremely high thermal conductivity, approximately 2000 to 3000 watts per meter per Kelvin for multi-walled CNTs. Their high aspect ratio allows heat transfer over long distances without requiring numerous particle-to-particle contacts, making them particularly effective thermal fillers. However, CNTs tend to agglomerate because of strong van der Waals interactions and poor dispersion in polymer matrices. Proper surface functionalization and dispersion techniques are therefore essential for maximizing their effectiveness. CNT-filled adhesives are often used in high-performance structural applications such as aerospace components, including aircraft wings and fuselage structures. Carbon fibers. Carbon fibers are less frequently used as fillers than CNTs because of their larger diameter and lower mechanical reinforcement efficiency. Nevertheless, they offer several advantages, including lower cost, good thermal conductivity, and high aspect ratio. An additional benefit is their negative thermal expansion coefficient, approximately -1.5 ppm per Kelvin in the longitudinal direction, which can offset the positive thermal expansion of polymer matrices and improve dimensional stability in thermal management applications. Diamond fillers. Synthetic diamond powder exhibits extremely high thermal conductivity, often exceeding 2000 watts per meter per Kelvin for highly purified materials. As a result, diamond fillers can significantly improve heat transfer within adhesive systems. However, the thermal conductivity of diamond decreases with increasing impurities or temperature. Due to its high cost, diamond is typically reserved for specialized high-power electronic applications, such as thermal interfaces for metal heat sinks or advanced semiconductor devices. Hybrid filler systems. To further improve thermal conductivity, adhesives may incorporate multiple fillers with different sizes, shapes, or compositions. These hybrid filler systems offer several advantages: improved packing density of particles, formation of more efficient conductive networks, reduced material cost, synergistic enhancement of thermal properties, copper nanowires and graphene oxide. A hybrid system combining copper nanowires and graphene oxide nanosheets can significantly enhance heat conduction in epoxy adhesives. Copper nanowires provide highly conductive pathways, while graphene oxide sheets act as bridges connecting discontinuous networks. Graphene oxide also contains oxygen functional groups such as OH, O, and COOH that improve compatibility with polymer matrices, enabling better dispersion. Aluminium nitride and boron nitride. Another effective hybrid system involves combining micro-sized aluminium nitride particles with hexagonal boron nitride flakes. In such systems, larger aluminium nitride particles, approximately equals 10 micrometers, create the primary conductive framework, while smaller BN flakes, approximately 1 micrometer, fill interstitial spaces between particles. This hierarchical packing structure increases particle contact and enhances the formation of continuous thermal pathways. Alumina nanoparticles, MWCNTs, and micro-sized alumina. Thermally conductive adhesives can also contain a mixture of micro and nanoscale fillers. For example, spherical micro-sized alumina particles may serve as the primary filler, while alumina nanoparticles and multi-walled carbon nanotubes provide nanoscale bridging networks. MWCNTs form continuous conductive networks within the epoxy matrix, substantially improving thermal conductivity even at relatively low concentrations. Conclusion: thermally conductive adhesives are critical materials in modern electronic and structural applications that require efficient heat dissipation. Because polymeric adhesive matrices inherently possess low thermal conductivity, the incorporation of thermally conductive fillers is essential for improving heat transport. A wide range of filler materials, including metallic, ceramic, and carbon-based particles, can be used to enhance thermal conductivity. Metallic fillers such as copper, aluminium, and silver provide excellent heat conduction but also introduce electrical conductivity. Ceramic fillers, including alumina, aluminium nitride, boron nitride, and silicon carbide, offer a balance of high thermal conductivity and electrical insulation, making them especially valuable in electronic packaging applications. Carbon-based fillers such as graphite, graphene, carbon nanotubes, and diamond exhibit exceptionally high thermal conductivities and are increasingly investigated for use as advanced thermal interface materials. In addition to filler composition, parameters such as particle size, morphology, Aspect ratio, dispersion, and concentration significantly influence the thermal performance of adhesives. Hybrid filler systems that combine multiple materials and particle sizes have emerged as a promising strategy for achieving superior thermal conductivity through optimized conductive networks. Overall, advances in filler design, nanoscale materials, and hybrid composite architectures continue to drive the development of high-performance, thermally conductive adhesives that meet the growing thermal management demands of modern electronic devices and high-power technologies.